Okay, we've been talking about colligative properties with non-electrolytes. What if you have strong electrolytes? Well, so the strong electrolytes separate into ions, you get more particles, right? So if we think about sodium chloride, right? You put a mole of sodium chloride into water and it separates into sodium ions and chloride ions. If you have 1 mole of that, then you're going to have 1 mole of this and 1 mole of this, and that's going to get you 2 moles of particles. Because colligative properties, it's the number of particles, it doesn't matter what they are. So this is what we would expect, that we get 2 moles from 1 mole. Well, it turns out that nothing's quite that straightforward. The Van 't Hoff factor, which is given the symbol I, which is different than the math I, it's the ratio of the moles of particles to the moles of formula units dissolved. And the reason these are not the same as the expected value is that some ions effectively pair up in solution. So here we have an illustration of a sodium chloride solution, and even though the sodium and chloride are surrounded by water molecules, they can still kind of be attracted to each other and want to hang out together. So if these guys are hanging out together, then they're going to act like 1 particle instead of 2. So these are the expected Van 't Hoff factors, and this is the actual Van 't Hoff factor. The actual measured factor is always smaller than expected. You do not need to know these measured ones. If you need it, it will be given in the problem. You could be expected to do a calculation where you would use the expected value, not the measured value. And so there you're going to look at the chemical formula and ask yourself, well, how many ions are in this unit, right? FeCl3, there's 1 iron ion and 3 chloride ions, and so 1 plus 3 is 4. So if we're doing ionic solutions, strong electrolyte solutions, we can take these 3 equations we just looked at and we can just multiply by the Van 't Hoff factor to adjust it for it being an electrolyte. So what's more important than really being able to calculate those is recognizing things like this. Which solution would have the highest boiling point? These are the same molarities, right? This is a sugar. You don't need to recognize that, but that's a molecular compound, not going to separate into ions. These are 2 ionic compounds. The higher boiling point will be the solution with more particles. Well, this is not going to separate into more particles. This could separate into 2. How many is this going to separate into? 3. So this is going to have more particles, and so that would have the higher boiling point. Does that make sense?
So it's only pertains to ionic.
Yeah, only ionic compounds. That was great timing.
Couldn't do that if you tried. Open the door right as the train whistle goes off.
I don't feel like doing that calculation. So there. The train agrees with me. Strong electrolytes are also going to have a larger effect on vapor pressure. And there's an example calculating the vapor pressure. I don't want to do that one either.
Tomorrow, that's okay.
Yeah.
Can we just skip the rest of them?
No, there's a couple of good things coming up. Okay, so why do we care about this at all? Okay, there are a lot of Chem 1A students are headed into the medical field, right?
Yay.
And so osmotic pressure is an important thing in medicine. Because if you give someone an IV fluid and the fluid has too many particles in it, right, it's going to cause osmosis into or out of the patient's cells. And we can see this with the blood cells. Okay, So this is what a normal red blood cell is supposed to look like. And so when they give you IV fluids, they're going to give you something that's like 0.9% sodium chloride solution. It's called normal saline. That has the same ionic strength or the same osmotic pressure as the fluid in your cells, what's inside your blood cells. So if we have hyperosmotic, it has a higher osmotic pressure, that's going to cause water to come out of the cell. And so you're going to have your blood cell start to kind of shrink up, and this is called crenation.
Looks like a ghost.
I know, and it looks kind of spiky and uncomfortable too. That's, this just can't be a good thing. And if you have hypoosmotic or hypotonic, like if you put pure water into somebody's blood, really bad, right? So the water's going to go into the blood cells, and it's going to cause them to balloon up and eventually burst. Right? Not good.
Someone with a nurse,
Mhm.
and she did that.
Oh
So funny.
no! Did they die?
Yeah, the lady was like, patient was 72 or something like that. By the time she realized, or we all realized, she was already gone.
Oh gosh.
Yeah, she definitely got sued.
Yeah. And see, sometimes chemistry students are like, well, it was just a little mistake, right? I had the right idea. It's like, well, yeah, you want to go be a nurse? You want to go be a doctor? That little mistake
Yeah.
is life and death, right? You're 1 decimal point off in calculating how much morphine to give somebody. You just killed them, or they're suffering unnecessarily and not getting any pain relief.
But like that's why like now, or I've seen more of lately, they have to have a nurse with them to scan.
Yeah.
Like you're not allowed to, which is, like you think it's juvenile. It's like everybody knows what saline is, right?
Yeah.
Because there's been a lot of accidents lately.
Well,
with them
because
giving too much.
we are human,
You gotta
right?
co-sign- yeah, you gotta
And
co-sign.
sometimes it's like, well, I could swear I put this here. Or you read something like pull on the door and you push, right? It's like, why did I do that? Well, our brains just make mistakes sometimes. And so then, they found ways to eliminate some of those mistakes. But so osmotic pressure is an important thing in the medical field. So what you want is isoosmotic. The osmotic pressure matches bodily fluid. And so normal saline is 0.9 grams of sodium chloride per 100 milliliters of solution. That's a mass to volume. And that is a common unit used in medicine. Why? Well, it's easy to make a solution like that. You can weigh out 0.9 grams of sodium chloride, and then you have a container that you can fill up to 100 milliliters, and then you shake it all up, and bingo, you have normal saline, right? They don't care how many moles are in there, right? So medicine uses a lot of things like percent mass to volume or mass of solute to volume of solution.